The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So we study group theory not to admire group theory, but to use it to make sense of spectra. And usually when it's taught as a separate and beautiful object. And the goal of trying to use it to ask the kinds of questions that we would want answers to as practicing spectroscopists is usually hidden. And so what do we want to ask? We would like to know from how a spectrum appears what it tells us qualitatively about the molecule. And as much as possible, I'm going to be trying to address that. And one of the most important techniques is creating a reducible representation using cartoon-like ideas and reducing it so that we can figure out what are the vibrations of the molecule, and then we find out what are their symmetries, and then we find out what will their spectra look like, because a given vibrational symmetry implies a certain rotational structure in the spectrum. And there are beautiful examples in the literature of the use of this kind of logic to decide on the shape of a molecule. And we will soon be starting talking in a case study way of electronic spectra. And one of the most beautiful things that happened about 60 years ago was the proof that acetylene undergoes a qualitative change in geometric structure upon excitation from the ground state to the electronically excited state. And that this could be proven by the selective use of group theory. A similar thing happens with formaldehyde, although the change in structure is not so dramatic and it's more subtle. And that is, formaldehyde in the ground state is planar, and in the excited state it's bent, but the barrier to planarity is very low. And so one uses group theory to look at the spectrum, and you see two different answers depending on whether you're looking at low vibrational levels or higher vibrational levels. So I hope that I will be able to give enough tools so that you can see how we get the qualitative information quickly. Okay, so here is a character table, and the reason I chose D3H is because it's not C2V. And everybody can do C2V, and there isn't much there. And this is one of the smallest groups that has degenerate representations. And so it's degenerate representation. Well, you can see how well prepared I am. So this is sufficient to illustrate as much of the complexity of group theory as I would hope we'd need. Now, so we have a character table, and these are the irreducible representations. And the first thing to notice is that the symmetry operations are arranged according to classes. I told you what a class is and how to find all the members of a class. But you can, yeah. And so there's 1, 2, 3, 4, 5, 6 classes. And these are the irreducible representations, and there's 6 of them. The character tables are always square when they're arranged according to classes. There's the same number of classes as there are irreducible representations. Okay, now the irreducible representations, the characters for them, are like a set of normalized, well, they're not normalized here, but they're like, they're orthogonal vectors. And they are normalizable in the sense that if you recognize that each element appears the number of times that there are members in a class, and you divide by the order of the group, then they are normalized. So one can always generate a character table by knowing the dimension of usually what you would do is you'd find out how many classes there are, and then you say, okay, I need that number of irreducible representations. And it doesn't take much to recognize that you're going to have two doubly degenerate representations. So you start with the totally symmetric guy, and you write as many orthogonal vectors as you can, knowing some rules. And you could generate this, and then after you've done that, you say, oh, well, now how do I put the different labels on these things? What are the characteristic features that are associated with each label? And I thought I knew that until I discovered that my rule about sigma v was wrong. Okay. In addition to, I mean, you don't need to generate all of these characters, because unless you're on a desert island and you don't have a book, the character tables are ubiquitous. They're everywhere. And so mostly what we want to do is know how to use these things. Okay, the character tables are dressed up with extra symbols in the columns on the right and more over here. And these are what you need for describing the selection rules for electric dipole transitions. And the thing that I didn't put over here are for Raman transitions. These are also things, the X, Y, and Z tell you about p orbitals. These tell you about d orbitals. So there's all sorts of things that you can use these character tables for. Okay. So one of the first things we want to do is to discover how, I mean, suppose someone gives you a character table like this without these things, to discover how rotations and translations, what do they correspond? What irreducible representations do they correspond to? And so you always want to draw a cartoon. And you want to know how to use these cartoons. And this is true for CNPI group theory as well as point group theory. And there are some very beautiful cartoons for classifying things according to irreducible representation in Bunker and Jensen. But I mean, suppose we have an axis system, X, Y, Z, and we would like to, so here we have a vector pointing in the Z direction. And so we'd like to know what the various symmetry operations do to a vector pointing in the Z direction. And so the first thing is the identity operation leaves it alone. A rotation by about the z-axis leaves it alone. It's still pointing, I mean, so the issue would be, is it pointing this way, that way, or this way? And so that you could have, all right, so C2, perpendicular to the symmetry axis, well, that turns it over, so that's -1. Sigma H, well, that's a reflection in this plane. That turns it over, -1. S3, well, that leaves it alone for the rotation part and turns it over for the other part. And sigma V, that's a reflection in a plane containing the z-axis. That leaves it alone. So here are the 6 things that happens to a translation in the z direction. And so we look for an irreducible representation that behaves that way. And it's not that one. It must be 1, 1. this one, A2 double prime. And that's right. And so I suggest that you do the same thing for a vector pointing in that direction and see how that behaves. And what you end up discovering is if you have a vector pointing in the x direction, it gets mixed with a vector pointing in the y direction. And you find that x, y together behave as E prime. So then there's rotations. Suppose we have a rotation about the z-axis. And now we ask, well, what do the various symmetry operations do to that object? And so a rotation, the identity does nothing. C3 does nothing. C2, perpendicular, well, that's going to take, now this is hard for me to see. It will, I think it reverses it. And so you have to practice a little bit. So you do this, and you discover that the rotation about the z-axis belongs to A2 prime. And so you can dress up the character table with these symbols, which are useful for telling you about selection rules. And we'll see how that works out. Okay. So one of the things you're going to want to do is compute the character of a direct product of two characters. So we have a character for so what do? You just multiply element by element and get a new vector. So for example, if we did E prime times E double prime, what are we going to get? Well, we're going to get 4 in the first position, and then lots of other stuff. And one of the things you know is that prime times double prime is double prime. And 1 times 2 is 2. And so there are a lot of things. A times B is B, and G times U is U. And so you know immediately that this is going to consist of nothing but irreducible representations that are double prime, and so on. Okay, so you do this out, and you get 4, 1, 0. Minus 4, minus 1, 0. Okay, so now we've taken a direct product of two E representations, and we have something that has 4 in the first position. This is reducible, because the highest order irreducible representations are of order 2. So we know that we have to take this apart into different irreducible representations. And what do? Well, we ask, well, how does this vector project, or how do each of these vectors project on this? And again, this is where you make the mistake. You have to remember that we're describing vectors that are associated with one thing for each symmetry operation, but we've condensed them according to classes. And so when you attempt to reduce this, you have to multiply by the number of elements in a class. So I've done the reduction, and so you discover that this gives rise to E. I can't even read what's in my notes. Is that a prime or a double prime? That looks like a double prime. It has to be a double prime. I said it was going to be a double prime. E double prime and a 1 double prime and a 2 double prime. So, I mean, one way to do this is you multiply this reducible character by each of these. But if you have some shortcuts, you don't have to do each of them. You just do the ones that you think are going to be important. And so this didn't require 6 direct products. You could have gotten it very quickly just with 3. And in fact, you could have gotten it with 2, because then you would know whether there's something left over. So anyway, this is the main thing. You get a reducible representation and you reduce it. And it happens again and again in various applications. Okay, so and this is one of the things that I really love about group theory. Dressing up a molecule with things that represent the internal coordinates or anything you want, and finding which irreducible representations do the things you picked out span. And so you can be, so suppose we have a molecule which is a D3H molecule that's planar and symmetric. And so boron trichloride is the molecule that everybody talks about, but CO3 double minus is the same thing. There's a bunch of these molecules. And so one of the things you can do is attach x, y, z coordinates to each of the atoms. So we have 4 atoms. So we have 4 times 3 Cartesian coordinates. So we're going to get a 12-dimensional reducible representation by just applying each of the symmetry operations to these Cartesian coordinates. And so you got 12 coordinates, and you do nothing. You ask, well, how many have been, everything is left alone. The matrix that did that was a matrix which has 1s along the diagonal, and it traces 12. The next thing is C3, and C3, perpendicular to the plane, permutes the end atoms, and so you don't care about them. So this is so easy. The only thing you worry about is what happens when you do a C3 for the atom that the C3 axis goes through. And there's a little trigonometry involved, and you discover that that has a trace of 0. So, and then C2 perpendicular, and there's 3 perpendicular C2s, and so those are a C2 that contains each of the atoms. These are permuted, and so they're gone. And now what happens when you rotate about this axis is you take you leave one of the coordinates alone, and you reverse the direction of the other 2, and so the trace for each of these is -1, and so we have -2. And so sigma h, everybody is involved. Nobody goes away, but 2 of the axes are in the plane, and 1 is perpendicular, and so 2 minus 1 for each atom. 2 minus 1 times 4 is 4, and so on. So you generate this reducible representation that contains everything that this molecule can do, which will be 3n minus 6 vibrations, 3 translations, and 3 rotations. Well, we got 3 translations and 3 rotations here, and so what we do is we reduce this, and that gives us all of the irreducible representations spanned by this Cartesian representation. And then we remove the ones that we have to, because those aren't vibrations, and we're left with something else. So we can determine very quickly that the vibrations generate the A1 prime, 2E prime, and 1A2 double prime. Okay, that's 4, 5, 6, the right number of degrees of freedom. So this D3H molecule gives rise to a total of 4 normal modes. Degeneracy is 6, but there are only 4, and not 6. And it might be a useful question to ask, well, can we distinguish between stretches and bends? Or can we divide this up in some useful way? So we could take a different representation and just say, okay, what about that? What about the stretches? And what did the group theory do for this 3-dimensional reducible representation?
What did you do with your razor?
I took away the Cartesian axes, and instead of having 12 things that we're messing with, now we have 3 things. Or I could also say 3. Now, these are not linearly independent, but you know that they can't all increase. That would be the totally symmetric representation. So you know that there are 2 linearly independent things you can do with the angles. So, but it's much more convenient to use this. And so you get 3, a total, you have a 3-dimensional reducible representation, and you take away A1 prime, and that tells you about the in-plane bends. You could also take a representation where here's the plane of the molecule, and we just put the z-axis through the center atom, 1-dimensional. And we ask, well, what is that? That'll be the out-of-plane bend, and that'll correspond to one of the irreducible representations. So as long as, if you can draw a cartoon-like object that enables you to sort the vibrations, you can begin to discover what is in each of these normal modes. Now, when you have only one of a particular symmetry species, you can be pretty sure that there is a unique conclusion about what that is that you can get from these cartoons. When there's more than one of a particular species, it tells you it's pretty likely that there won't be a segregation of stretches and bends. So this is beautiful because you didn't do anything. We didn't solve the GF matrix problem. We don't know what the S vectors are, yet we know what are the allowed symmetries of all of the vibrations, and we know whether some of them are pure stretches and some of them are pure bends, and even qualitatively what kind of bends. And you don't have to do anything, you don't have to be careful to avoid an overcomplete cartoon, because you can very quickly project out the piece that was associated with being overcomplete. And it's fantastic. And so once we have sorted things out, I mean, in this case we have A1 prime is a pure symmetric stretch. Well, that's pretty obvious because, you know, a symmetric stretch, you can look at that, you could say, well, that's got to be totally symmetric. And what's harder to say is, well, that's all it could be, that there's nothing else. But there's only one of them, and so it had damn well better be the symmetric stretch. And then the A2 double prime is a pure out-of-plane bend. And so the 2E prime representations are mixtures of stretches and bends. And one of the nice things about them is when you have a doubly degenerate representation, you can often draw a picture that, that suggests the molecule is doing something that looks like an angular momentum. So here's a picture, and what I've done is I've made one of the angles small. And now I'm going to draw the same picture, except that now I'm going to make this angle small. And then another picture that makes this angle small. So what you have is a distortion of the structure that looks like it's rotating. That's called pseudo rotation. And you can do the same sort of thing with the stretches. You can say, okay, I've got a stretch where I've elongated this guy, and then the next cartoon I've got a stretch where I've elongated that guy, and then the next one I've got a stretch where I've elongated this guy. So it looks like the molecule is rotating again. And you can go in both senses. That's why it's a doubly degenerate representation. So you have a kind of vibrational angular momentum, which isn't an angular momentum. And there's two senses. And so those are called pseudo rotation. And that's an interesting thing.
You mean in both senses you could be stretch and bending?
Well, you can mix them together too. But I mean, just have these two pictures. You can have first this one, then that one. Or you could have first this one, and then somebody that's distorted in that direction. So you can have the distortion going around this way, or you can have the distortion going around that way.
Couldn't you also have one distortion going in one direction and another distortion going in another direction?
Sure, you can have any linear combination. You have a doubly. You can take any linear combination of them, it turns out that often when there are these pictures that say, okay, there's a distortion that's moving around the molecule without the molecule rotating, it's like an angular momentum, and you use ideas of angular momentum to get splittings in the spectrum. That's a little bit beyond my pay grade right now because I don't understand that well enough to lecture. Okay, so now we have determined the irreducible representations. And now what we want to do is find out, well, what are the spectra going to look like? Can we tell whether this molecule, BCl3, is planar or something else? And so if it's planar, it's obviously an oblate top. If it's distorted from planar, it can be oblate or prolate. But so we have D3H, and then we have C3V, oblate or prolate limits. And then there are lower symmetries still. And so what you often do when you don't know what the symmetry of a molecule will be is you say, okay, there's a reasonable sequence of possibilities. And I do the group theory for each of them. And I look for features in the group theory that will say, this is where I can tell the spectrum, I can tell from the spectrum which point group the molecule belongs to. And that's kind of neat. And I wish I could do this smoothly and cleanly to impress you with how informative it is, but let's see what we can do. So the thing that makes transitions occur is the dipole moment function. And this dipole moment is a function of the coordinates, and it's a vector, and we can write it as a sum of components where we classify the components according to the inertial axis system. Okay, and so we're interested in this vector, and we're resolving it according to the 3 principal axis components. These are unit vectors. And so we have the equilibrium geometry, the A component of the equilibrium geometry. And then we have the first term in the power series expansion. Evaluate equilibrium, etc. Okay, and so these are the permanent dipole moments along the principal axis system, and for this molecule, you know, at least in D3H, you know that all of those are 0. These are the things that gives rise to a pure rotation spectrum. And so if the various geometries will have some non-zero permanent dipole moments, one can resolve the question simply by looking at the rotational spectrum. But usually the interesting stuff, and there's much more information coming from the vibrational spectrum. So these are controlling the intensities of the vibrational spectrum. And so what is this? This M is the result of an integral. Or this partial derivative of M is the result of an electronic integral. So we know that this quantity, partial M ABC dqi, is an integral that contains the partial derivative qi. It contains psi star, the jth electronic state, and A, B, or C, and psi j d tau. So we want this integral to be non-zero. Now, this is a vibrational spectrum, so the electronic wave function is the same. We use so this is automatically totally symmetric. This has the symmetry of the ith normal coordinate, and this has the symmetry of Rx, Ry, or Rz, but we have to make a correspondence X, Y, Z, A, B, C. And that correspondence, there are often many different or several different geometric forms that are consistent with a particular point group. And so you have to worry about how do the Cartesian coordinates in terms of which the point group is expressed, how do they map onto the principal inertial components? Josh?
Did you mean X, Y, and Z instead of Rx, Ry, and Rz in the middle of that integral there? You said those map to Rx, Ry, and Rz. Do you really mean X, Y, and Z?
These are rotations. I haven't thought about this in fighting detail for 12 years. It was my impression that I want Rx, Ry, and Rz here, but I might be wrong. So it's a good question. I can't answer it. So what we want is, since these have belong to the same irreducible representation, in order for this integral to be non-zero, we want the normal coordinate and whatever symmetry species these are supposed to refer to be the same. And so let's think about this. It's X, Y, and Z. It is X, Y, and Z. So this then tells us which one of these survives, and that determines the rotational structure. Thank you. I stared at this a long time last night, And I thought I had it, but that was the one thing. Okay, so we're okay. So now we know that the derivative with respect to qi, that's the same symmetry species as qi, and so we then look at the transition moment, the three possibilities for the transition moment, and so the normal mode, the normal coordinate here has to correspond to one of these three, and that then determines what are the allowed transitions and how does their rotational structure behave. So we have three symmetries. And we have E prime twice. And so there is no symbol opposite A1 prime. And so this is vibrational forbidden. The fundamental for this mode is a transition between a totally symmetric level and another totally symmetric level. And there is no x, y, or z opposite that corresponds to totally symmetric. So this mode is not going to appear in the infrared. This one is A2 double prime, that's z. So that is going to appear. And E prime is here, and that's xy. So we have, in the spectrum, we have one normal mode that's going to be z-polarized, or is going to have a rotational structure that's associated with a z-dipole, a z-changing dipole, and two doubly degenerate vibrations that are going to be associated with the perpendicular. Okay, so now for this, the c-axis is the z-axis. So for a symmetric top, which is oblate, the symmetry axis is going to be, so that's the highest order rotation, and that's going to be the C inertial axis. For a prolate top, the symmetry axis is going to be the A axis, and that would be Z. Okay, but we don't have a prolate top here, and it's fairly hard to make this have a shape that looks like a prolate top. Okay, so C is equal to Z, and it doesn't matter whether X is A or X is B. And in many cases, because it's a doubly degenerate group, a doubly degenerate irreducible representation, there's almost always a problem about ambiguity about what do X and Y correspond to. And the only cases in which you have problems is when you have B1 and B2 irreducible representations. And that happens in C2V. And there needs to be a convention about which is going to be X and which is going to be Y. And I believe X is out of the plane of a planar molecule. And but there is an agreement on that, and I always forget it. I used to not forget it. I'm too old to remember these things. Yes.
I have a question.
Yes.
Why do you use the molecule fixed axes instead of the lab fixed axes? Well, I guess the dipole moment is in a particular direction in the molecule.
That's correct. And so, you know, once we get rotations, rotational wavefunctions are really the transformation between the laboratory and the body. And so the information, once we specify where the dipole is in the laboratory, in the molecule, then the rotational selection rules give tell us about the relationship between the laboratory and the body. Okay. Now we don't care about the polarization along the X, Y, and Z axes in the laboratory, but we do care about how the transition moment in the body frame. Yes. Okay. So it's a good question, but I think that I think I've answered it in a fairly primitive way. Okay. All right. So for D3H, we have 4 modes, 3 of which are infrared active, and if I had filled out this table, I think we would have found that the other one is Raman active, and there is a general rule about complementarity, or there is a rule, and in certain symmetry species, if it's, no, I better not say, I don't know. But often you get, if there's a mode that's forbidden infrared, chances are it will be allowed Raman. But even so, I mean, if you have too many irreducible representations, there's no guarantee that all modes will be allowed, both taking together infrared and Raman. So let's just be careful about that.
Do these labels about the polarizability also tell you about the quadrupole?
Yes. Yes. So these tell you about electric dipole. These tell you about magnetic dipole. Then there's the quadrupole. There's all sorts of things. So you learn to use whichever symbols are relevant to the kind of spectroscopy you're doing. Okay. So one of the important things is, here is a transition that is polarized in the body along the symmetry axis. And so we call that parallel. And here's something polarized perpendicular to the symmetry axis, and we call that perpendicular. And this is all the difference in the world as far as the rotational structure of the bands is going to be. And we saw that for diatomic molecules. We had transitions that were parallel, delta omega equals 0, and they don't have Q branches. Or they have really weak Q branches. Perpendicular transitions, they have delta omega plus or minus 1. And they have strong Q branches. And so this is going to be delta K equals 0. This is going to be delta K equals plus or minus 1. This is going to have no weak Q branches. This is going to have strong Q branches. Okay. So the traditional way of making sense of what you're going to see in the spectrum, all the textbooks have to do with an ordinary low-resolution spectrum, which you would record using a spectrograph rather than a laser. And so I'll start with that. But you should think, when you're doing laser spectroscopy, it's usually difficult to tune the laser over a lot of spectrum. And often you want to get the answer about what is the assignment of the spectrum, what is the symmetry of the molecule, based on a limited amount of spectroscopic observation. And the kinds of questions you ask would be different. This would be a legitimate kind of problem, but I haven't completely formulated it. So I will draw the pictures, the traditional pictures, but you should think about, well, what would how would you use group theory to get a little bit of spectrum and decide from a little bit of spectrum what the molecule is doing? Okay, so remember when we talked about infrared spectra of molecules, we drew this sort of double hump pattern. And so if we have red on the right, so this would be the R branch, and this would be the P branch. And if it were a perpendicular transition, which was kind of hard to imagine for a diatomic molecule, but then you would have a Q branch here. So that there is a gap near the origin of the band, and if there is going to be a Q branch, it'll be close to it. And the R and P branches are always spread out, and the Q branch is always compressed. So this is sort of a model for what we would have for polyatomic molecules. So if we have a parallel type transition, so parallel means delta K symmetry, whatever it is, oblate or prolate, is equal to 0. So we have so we have K equals 0, and then we have K equals 1. And so for K equals so in K equals 0, we have a stack of rotational levels. In K equals 1, we have a stack of rotational levels. And so we're going K equals 0, lower state, to K equals 0, upper state, rotational levels. The rotational, the J structure of a given K is pretty much the same from one vibrational level to another and from one K stack to the next, except that the lowest few J's are missing for K not equal to 0. And so if you're going to be doing a laser experiment, one thing you could do is make sure the molecule is really cold. And so that clears away a lot of the rubble. And then you would be looking to see what is the lowest J you have in a particular series of lines, which you do by combination differences. And you
just rotational cold in B.
Yeah, that would be one way to do it. Now, one really important thing is that for a prolate top, the J structure is smaller than the K structure. For an oblate top, the J structure is larger than the K structure. But for both kinds of tops, if you have a parallel transition, the 0 to 0 transition and the 1 to 1 transitions are going to be almost on top of each other. For symmetric tops, you can observe multiple Ks, but you can't observe transitions between them, and they all stack up. And so for a parallel type transition, all of the different K subbands look roughly like this. They have this double hump structure. There's missing stuff in the middle. And there could be a Q line. The Q line is generally weak, but it turns out that when K is not equal to 0, there will be one moderately strong Q line for J is equal to K. And so the parallel bands have the appearance more or less just like this, as if it was just a simple diatomic, except that there's a lot of lines. And so you see this simple double hump and a little bit of a spike here. So one of the bands is going to look like this. And perpendicular transitions, those are going to be transitions where you go from K equals 0 to K equals 1, and K equals 1 to K equals 0 and things like that. So there's going to be a whole bunch of bands. This time, each of them is going to have a big spike here because the Q branches are strong. And so the question is, how do these bands, how are they arranged? And they're arranged, basically you have, for a prolate top, you have CK squared. And so you'll have a transition that goes from 0 to 1, and from 1 to 2, and from 2 to 3. 0 to 1 is going to be 1, is going to be 0. So let's just draw this arrow like that. So this will be 1 squared minus 0, 1a, 1c. And this is going to start at 4 minus 1 is 3c. 9 minus 4 is 5c. So what you're going to see is a series of subbands separated in intervals of 2c. So, and you can go 0 to 1, or you can do, you can go in the opposite direction. And so there'll be bands, there'll be subbands with Q branches going one way and Q branches going the other way. And so what do? How do we denote those transitions? So we have a notation, delta J, delta K, K initial. And we put J here. So that's how we denote the name of a rotational line. So we use PQ and R for delta J. We use PQ and R for delta K. We specify the number of the initial K and the initial J. The double prime is not a symmetry label, it's initial state. Lower state. I'm sorry, lower state. Double prime, lower state. Single prime, upper state. So this is a very convenient notation that will enable you to label every line. Okay, and so what you can discover, I mean, if you're doing relatively low resolution spectroscopy, the thing that's going to stand out is the Q branches. And so there'll be a series of equally spaced Q branches associated with each of these K transitions. And so on page 7 at the top, I show a bunch of spectra, each like this, but the whole spectrum shifted in steps of 2c this way and that way. And then I just take those spectra and add them together, and I see a series of equally spaced Q branches with a lot of trash. And so that provides you with the signature of a perpendicular transition in a symmetric top, this series of strong Q branch spikes. And whereas a parallel transition has just a single hotspot in the middle, not quite so compact, and since the Q branches are relatively weak, that hotspot in the middle is not overwhelmingly stronger than the other lines, but because they tend to be a little bit closer together, it's still pretty prominent in the spectrum. Okay, what time? How much time do I have?
-4 minutes.
-4 minutes.
That's not true. You have 5 minutes. Yeah, we started at 10.
Okay, so there are a whole bunch of pictures that you can draw for the various symmetry types of transitions. Now, if you say it's not D3H, it's C3V. C3V still has E representations, but it's a group of order 6 instead of 12. And but you can still do all of this stuff. But then there's two possible C3Vs. There's a C3V where it's a prolate top, and there's a C3V where it's still oblate. And so, and they will have different looking spectra. It's primarily because an oblate top is going to have is going to have K structure, which is really small compared to rotation, and the prolate top will have K structure, which is large compared to the J structure. So there's all sorts of wonderful things you can do. Now, on page 9 in the middle, there is a little piece of a somewhat higher resolution spectrum, which shows the K structure. So this is a parallel type band, and the caption is the K structure of two rotational lines in the CH3BR nu 3 mode. Okay, there's all sorts of wonderful stuff here. First of all, two rotational lines. That means two changes in J. P17 is J equals 17 downstairs to J equals 16 upstairs, and P18 is the next one up. And there's a whole bunch of labels on that corresponding to the different Ks. This being an oblate top, it's not an oblate top. This being a parallel type transition, it's a prolate top because the hydrogens are light and there's one bromine. If it were CBr3H, probably oblate. But the different rotational transitions for the different Ks are clustered together. And so that is would be a characteristic structure for a parallel type transition. And so anyway, you do this group theory and you try to find what's going to be different for one symmetry species versus another. And one of the commonest things is the number of discrete bands that you can see for the molecule depends on the symmetry, on the qualitative structure. And so if you observe, if it's D3H, there's going to be 3 allowed vibrational fundamentals. If it's a lower symmetry, there will be a different number. And then there's the question of parallel versus perpendicular. And so you can tell from the nature of the band. Then there's this business of asymmetry splittings. You have a particular J, K, A, K, well, J and Ka. There's 2 Kcs associated with that. And we know just from consideration of the rotational constants, the A, B, and C, that the one where Ka plus Kc is equal to J is higher than the one where Ka plus Kc is equal to J plus 1. And so that is always going to be there. And depending on the symmetry of the vibrational level, you will have transitions selectively into the upper or lower that you can tell the difference. And that, I didn't say that very well, but that turns out to be a really important marker because this ordering of the J, Ka, Kc levels is an inertial effect as opposed to some accident. In diatomic molecules, lambda doubling is an accident. But this is something that you can depend on. There's another thing, and that's nuclear statistical weights. That if you're permuting identical atoms, you're going to have to worry about the permutation symmetry. And so there will be ortho levels and para levels. There will be intensities that alternate or do something as a function of J and K that is uniquely recognizable. Now, I'm never going to talk about the nuclear statistical weights in this course, but that is a really important feature, and it's especially important. It's best dealt with in CNPI group theory because it forces you to make cartoon representations of the things that where you can build ortho and para states, states that with definite nuclear symmetry. And I mean, I can challenge you. How do you classify the levels of acetylene where you got 2 identical bosons and 2 identical fermions? And you know, that's a non-starter. You don't know what to do until you develop a generalization and you say, okay, I need two structures. I need to label them 1AB2 and 1BA2, and then I can build states that have the right, out of linear combinations of those two structures, I can build the states, and then I can classify them according to whether they're like ortho or para. So that's something that I wish I could talk about, but I want to move to electronic transitions, and that can only be dealt with in a case study way, and so that's basically what we're going to be doing for the rest of 580. So thank you for being patient with my lack of precision on this topic, but it's a fun topic and you should explore it. And I was thinking about a molecule, and so, trimethylcyclopropenyl was a candidate. But I don't think I'm going to ask you to do anything like that. But it's a good molecule because it's basically this molecule, but it's got some hair. Okay.
I had a really quick question, maybe.
Yes.
About pseudo rotation.
Mm-hmm.
If you are an observer,
yes,
you presumably can't tell the difference between rotation and pseudo rotation if the molecule is really symmetric, right? So,
well, what are you observing? You're not watching the molecule move. You're not looking at the wave function. You're looking at the spectrum.
Right. So that was sort of what I was about to ask.
Yeah.
So let's say that I apply some time-varying field to the molecule that ought to induce pseudo rotation, if one can imagine such a thing. Maybe one can't because it's totally symmetric.
I think that would be hard, but one of the things that you do have is when a molecule is rotating, that distinguishes left rotation and right, so that you end up, as soon as the molecule is rotating about an axis, that splits these, or can split these pseudo-rotating states in a way that is understandable. Now, Dick Lord, who was, my predecessor as a spectroscopist at MIT, and he made his career on pseudo-rotation for ring puckering motions, so that you'd have a let's say cyclohexene, and so you have this chair, but this chair and boat conformation can
Swing around,
yeah, and so there are all sorts of wonderful things like that. But as soon as you introduce rotation, then the left and right, the counter and clockwise and counterclockwise rotations get distinguished in terms of Coriolis effects, and so, but that's really complicated. Okay.